Good afternoon. We are filming another video lesson for plate tectonics. By the way, the plate boundaries are on an already existing video that you already have access to on Canvas. Okay, so we're kind of going to do a little bit of history lesson in this video lesson. All right, first of all, what is the name of our most recent supercontinent? That is called Pangaea. That's a term you may have heard before. Pangaea was fully formed by about 250 million years ago and started breaking up about 200 million years ago. Rodinia, or Rodinia, is the supercontinent before Pangaea. Yes, there were at least two. Are these exam questions? Of course they are. Otherwise, I wouldn't have bothered to write them on the board. All right, so now we're going to take a look at Alfred Wegener. So he was a German meteorologist, and he was a science nerd, and well, he went on at least a couple of expeditions to Antarctica, and he did a lot of library research, and he basically read about research that other people had done looking at things like fossils on different continents and evidence of past conditions. Anyway, so back around 1914, I guess it is, he first wrote up his hypothesis of continental drift. By the way, we called it continental drift back then. Now we call it plate tectonics. Well, at the time, you would think that this would be revolutionary and everybody would jump on board, but they did not. And he was ridiculed by other scientists because he could not explain the mechanism for continental drift. He couldn't tell anybody what was a powerful enough force to move continents. Of course, we now know that it's not just the continents, but the plates that move around, be them continental or oceanic, and we now know that he was correct. And we now know the driving forces on the plates, and that's something we will cover in the narrated PowerPoint for plate tectonics. All right, moving on to a discussion on the evidence that Alfred Wegener gathered for continental drift. Okay, so what was likely obvious to lots of people that ever looked at a map or a globe is the obvious fit of the continents, as in they match up, and they actually fit better if you fit them at the edge of the continental shelves instead of where the water level is today. But even just looking at where the water level is today, and you look at a map, for example, it's pretty obvious that South America and Africa used to be together. So what else, what were some other lines of evidence? Well, matching non-marine fossils, as in fossils that could not swim across ocean basins. We found some of those same land-based fossils spread out on most of the different continents. Again, in the narrated PowerPoint, we're going to elaborate on this a whole lot more, and you will see some really cool images to go along with this. What else? How about matching mountain ranges? Say the Appalachians matching up to mountain ranges found in Western Europe. And how do you match mountain ranges? Well, it's not enough to just look at maps or look at them in a satellite image. You have to go to those mountains. You have to take samples. We matched up rock ages and rock types. And then there were several lines of matching climate evidence. Glacial deposits from past glaciers, coal swamps, reef limestones, desert dunes, salt deposits, and continental shields. So again, when you watch the narrated PowerPoint for plate tectonics, as I expect everybody to do, we will elaborate on these things. The video lessons are meant to be short. Otherwise, it would take like 24 hours to upload it to YouTube. Okay, so we are now going to go a little more recent in time to World War II. So what did World War II have to do with plate tectonics? And the answer is, well, plenty. Okay, so in addition to the Allied powers fighting the Axis powers, and of course eventually we did win the war, thank goodness, the Allied powers, not just the US. Anyway, in the process of fighting enemy subs in the Atlantic and Pacific, we pretty much accidentally mapped the ocean floor. We refer to that as bathymetry, or those underwater maps are bathymetric maps. Certainly we weren't out there to do science. We didn't have time for that. We were trying to win the war. So what kind of things did we find? Well, we ended up discovering a lot more about the ocean floor than we had previously known. I'm going to adjust the iris a little bit because I think it might be a little too bright. Let's try that. Okay. We found mid-ocean ridges, which are underwater volcanic mountain chains, like the Mid-Atlantic Ridge. We found abyssal plains, which are these flat, featureless parts of the ocean floor. We found deep ocean trenches, like the Mariana Trench, which is the deepest part of any oceans on this planet. We found fracture zones, which are basically big strike-slip faults that offset segments of the mid-ocean ridges. And we also found seamounts. Now, seamounts are extinct underwater volcanoes that probably rose above wave base and were islands back when they were active. We'll discuss the seamounts a little bit more. We'll discuss all of these things more in the narrated PowerPoints. And then we'll discuss the seamounts more towards the end of that PowerPoint where we talk about hotspots and hotspot tracks. So our drawing here at the bottom, we're showing a submarine. And it's not two submarines. It's a submarine, a time 1 on the left and a time 2 on the right. And what we see there is part of the ocean floor. So at time 1, over on the left, our submarine is above an abyssal plain. So how do we map the ocean floor? Well, sonar. So we're using sonar to try to find enemy subs, and that involves making a sound, which we refer to as a ping, and then the sound leaves the sub and it travels through the water column at a known rate, and then when it hits something solid like an enemy sub or a big blue whale or the ocean floor, it's going to reflect and come back to the sub. And we then count the number of seconds it took, and we know how far beneath our sub this particular object was. Now, in time 2 is to the right, and the submarine is motoring along, and it's above this weird-looking feature that is representing a mid-ocean ridge. So, what I want you guys to do as you're watching this is try and determine, in time 2, when the submarine is over the mid-ocean ridge, is it going to take more time or less time for that sound to come back to the sub? You got your answer? Less time, because that object is closer to the sub. Okay, and basically this is how, using sonar to search for enemy subs, not only did we finally win the war, but we also mapped the ocean floor. And each one of these 5 things that we found is a part of the puzzle in trying to figure out how our planet works. By the way, plate tectonics is a very important unit, and it's a huge part of your exam 3, which is a whopper of an exam. And everything that I'm going to make in a video lesson and most of the things on the PowerPoint are going to be important for your exam. So let's move over to the next topic. All right, other discoveries during the 20th century that helped us move from the hypothesis of continental drift to the theory of plate tectonics. All right, so back maybe in the 60s, we discovered high heat flow at the mid-ocean ridges. And a famous geologist, his name was Harry Hess, you do not have to know his name, he figured out that the heat flow at the center of the North and South Atlantic Basin, that heat signature must be there because we have magma flowing up to the surface and then solidifying to create brand new oceanic crust. And guess what? He was right. We now know that. Something else that we did in the 20th century is plotting earthquakes and active volcanoes on a world map, and we discovered that it is a non-random pattern. In other words, there is a pattern to it. Again, we'll discuss this stuff more in the narrated PowerPoint. Seafloor drilling with fancy oceanographic vessels. The ability to drill down into the oceanic crust was quite helpful. Radioactivity in general was discovered, actually it might have been late 1800s. So it was in the 20th century that we perfected radiometric dating. In other words, trying to get an age date on old rocks. And we have been able to do this for both continental and oceanic rocks, which is how we came up with the age dates that you saw on one of your other video lessons. And then the last bullet there is a lot of fun. Marine magnetic anomalies, also known as seafloor stripes. And that, that is something I hope to cover in class together because it's very important. And we're going to see that the marine magnetic anomalies, or seafloor stripes, were so important because they helped prove seafloor spreading. So more on that in the narrated PowerPoint. All right, we are gonna skip back to the corner of our board here. And a few more notes before we are done with this lesson. So this will kind of be an intro to the video lesson on plate boundaries. Actually, I kind of hope you watch the video on plate boundaries maybe last. I'll try to remember to make a note of that in Canvas. All right, so the surface of Earth is broken up into many discrete plates. And at this point, hopefully you have watched the video lesson that includes Earth's interior, so you know what we mean by plates. So the intersection of either 2 or 3 plates is known as a plate boundary. There are plenty of plate boundaries on this planet. And, well, most of them are potentially dangerous. The mid-ocean ridges maybe not so much. So, some coastlines lie on a plate boundary and some do not. So the East Coast, that should say East Coast on the board, the East Coast, as in, you know, where we live, is not a plate boundary. Therefore, we're going to refer to it as a passive margin. Okay, so what does that mean? It means that while we occasionally have, you know, small to moderate earthquakes, we don't have near the earthquake activity that they do on the West Coast. And we most certainly do not have any active volcanoes. Okay, we might also think of the East Coast as a submergent coast. What does that mean, a submergent coast? Well, it means that sea level is rising, but the land is not rising. So the East Coast of the United States is not rising because we are not a plate boundary. So we will experience the full effects of sea level rise. We are a submergent coast. Now the Gulf of Mexico is, well, it's like a submergent coast on steroids. The Gulf of Mexico is not a plate boundary and it's not rising. The land is actually sinking there. So the Gulf of Mexico is a really good example of a submergent coast. Okay, so how about the West Coast? Well, it's different. Okay, so the West Coast does lie on a plate boundary. There are 2 plate boundaries out there. We'll talk about that, our last topic for this video lesson. And since it does lie on a plate boundary, we're going to refer to the West Coast as an active margin. Okay, what does that mean? It means that they have earthquakes all the time. I mean, small ones happen every day somewhere on the West Coast, and quite often they have them large enough to feel. I mean, once it becomes about a 3.0 and above, people are going to feel it. They have large devastating earthquakes from time to time, and there are active volcanoes in Northern California, Oregon, and Washington. Now, we may think of the West Coast as an emergent coast. Why? Well, it just so happens that the Pacific Northwest, Northern California, Oregon, and Washington, the land there is actually rising because of the plate boundary that is there. So the fact that the land is rising will partially offset sea level rise. Therefore, we refer to it as an emergent coast. But to be honest, sea level is rising much faster than the plates are moving. So we're now going to walk over to another board and cover our last topic for this video lesson. All right, so we're trying to cover things that we would have talked about in class if we were here together 3 days a week. Okay, so these are potential extra credit questions on your 3rd exam. The nearest plate boundary to the east, to our east, is the Mid-Atlantic Ridge. Okay, so the East Coast, again, is a passive margin, not a plate boundary. How far would we have to travel to the east to see a plate boundary? All the way to the middle of the Atlantic, to the Mid-Atlantic Ridge. That should say ridge. It's misspelled there. That's okay. How about to the west? Our nearest plate boundary to the west, well, we have 2 of them. We have the San Andreas Fault, which runs, say, the bottom 75% of California. And then north of San Francisco, the San Andreas Fault runs offshore, transitions into the Mendocino Fracture Zone, and then you have the Cascadia Subduction Zone, which runs from Northern California through Oregon and Washington. All right, and that'll do it for this video lesson. So we're going to have at least 3 video lessons for plate tectonics. Peace out.